OSPF Understanding Network Types. I have been waiting for this video. Since the whole bsci series started, this video has been in the back of my mind, knowing that sometime in this series we'd be getting here. And we're here. It is the OSPF network types, more specifically focused around non-broadcast multi-access networks, or frame relay clouds, ATM clouds, and so on. The reason I've been waiting is because this was the toughest concept for me to get when I learned about OSPF many moons ago. I can still remember thinking for months, like, what on earth was that about? Or why would I ever use that? It seemed like there was so much focus on these network types, and I didn't get it. And it wasn't until I got to the CCIE that I was really thinking, oh, that's why they have these network types. Because there's all kinds of weird situations where OSPF needs you to tune it and tweak it to work across different types of networks. That's what the focus of this video is going to be. Focusing in on, first off, what kinds of networks OSPF supports in general, and then turning our focus specifically on the 5 modes of operation it has for NBMA networks. Let's get going. Well, let's start with the good news about the OSPF network types. OSPF only supports operations across 3 different types of networks, and you already know about 2 of them. Broadcast multi-access, point-to-point, and NBMA networks, which these 3 network categories really encompass all the types of networks that are in the world today. So first off, broadcast multi-access, examples of that is things like Ethernet, fast Ethernet, token ring, and so on, and that is a single operation mode. It is known as broadcast multi-access. A broadcast reaches all clients on the subnet, and multi-access, all the clients can reach each other. Now, in that operation mode, there is a DR and BDR election, which you have seen. There's 10-second hellos, so 40 seconds until the dead interval hits, and that there is dual multicast addresses. 224.0.0.5 reaches everyone. 224.0.0.6 reaches the DR and BDR. So that mode is boxed up, put with a little bow on it, and shipped along. Second one, point-to-point. You've already seen. Examples of that is T1 CAS, ISDN, BRI, just anything that has a point-to-point connection, typically WAN links. It is a single operation mode. There is no BDR and DR because they said, why have an election when there's only 2 routers on a point-to-point link? 10-second hello interval, 40-second dead interval, and everything is sent to a single multicast address, 224.0.0.5. The last one is what this entire video is about, and that's the bad news. NBMA networks are wacky, and OSPF's way of dealing with them are equally wacky. Examples of NBMA networks are things like X25, frame relay, ATM, those style of networks where you have a cloud. And things don't physically have connections together, they really connect via PVCs. In the OSPF specification, in the industry standard specification, there are 2 modes of operation. Cisco said, we'll make it a little more featurific and add our own 3, and now we have 5 total modes of operation, meaning methods or strategies that you can use to make OSPF work properly across those networks. That's what this whole video is about. The reason OSPF is so weird across NBMA networks is just the fact that they're weird in and of themselves. They're so sublime. There's no real design standard that says you must run your NBMA network this way. So there's a whole variety of strategies that people approach this with, and all in those strategies come the budget, come the connectivity, come the redundancy, come the delay factors. All those pieces fit together, and people come up with one of these designs. If the IT people had their way, we would always have a full mesh NBMA style network, which means that every single site has a direct connection, a direct PVC to every other site. The beauty of this design is that no one router failure can cause an outage of the whole network. If this router were to go down over here on the left-hand side, wham, all the other routers can reach each other without a problem because they have direct PVCs to each other. So the benefit of a full mesh is that you have a huge amount of redundancy and there's very little delay, which has become a huge factor in voice over IP. In some of the other designs, you have to go through the central site to reach the other sites, which increase delay, and I'll talk more about that later. But as you might have guessed it, this design doesn't get used very often because it's costly. Every single one of those PVC PVCs has a reoccurring monthly cost. So sometimes people will negotiate on the partial mesh, meaning that some sites, the key sites, have dual PVCs or three PVCs that have connectivity, and maybe these are your major corporate offices that have redundant PVCs. So if any one of these sites fails, there's another path to reach them. However, there's this site down here, and it's just a few people down at the office. All they really do, it's in California. They just play online games all day anyway. So, they're not that essential. So if their site goes down, that's okay. So we only afford a single PVC to that location. Beware of the single PVC site. If you're working at a site that only has one PVC, watch out. So the partial mesh is kind of a good in-between. Now, the most common strategy that's used on Frame Relay and X25, these NBMA style networks, is this one. And you might have guessed it, it's because it's the cheapest of all of them. The star topology, most often called hub and spoke, where the central office that has the biggest router and all the major equipment and the most employees working at the site has all the PVCs. All the other offices go through this central office to reach each other. Now, the benefits are, in a huge way, the cost, because you only pay for a single PVC for each location. But there's no redundancy, as in if this router goes down, everybody goes with it. And there's delay considerations. With voice over IP, we have to travel all the way across the network, then back, just to reach the other site, which causes echo and problems like that when you get to voice over IP configurations. So because it's so, like I was saying, sublime, just kind of what design are you going to use? It's up to you. You can use whatever you want, and then take on top of that you can choose point-to-point and multi-point strategies. They had to come up with all kinds of methods that OSPF can use to run across those network types. With that being said, here are the 5 modes of operation that OSPF can use across an NBMA network. Now, this list of 5 is divided into 2 major sections. The first 2 are RFC standard, and that means that if you have non-Cisco equipment on your network, why you do that, I'm not too sure, but if you did, and they were running OSPF, they could speak to your Cisco gear using one of these 2 modes. The other 3 are Cisco proprietary methods, which, of course, only work if you have Cisco gear all around the board. Now, these modes, as I mentioned at the very beginning of this video, were one of the most difficult things for me when I went through OSPF, trying to understand it, and even getting to the CCIE level. In the CCIE lab, Cisco knows that these modes are just weird and confusing, and they all have different criteria. So one of the major tricks on the CCIE lab is trying to figure out which mode you have to use and how to configure that mode and all that sort of thing. And I think the reason it was so difficult for me is because for so long it was spoken about, and I saw this presented in a way that was just theory, meaning instead of seeing practical application, like here's how you'd use this, I just saw a theory like this is what this mode does, this is what this mode does, here are the criteria. So I'd like to try a little different approach. In this video, I'd like to show you each one of these modes, but show you them with configuration, as in here's a frame relay cloud, and if I wanted to use this mode, here's how I would configure it. Now, what I just said, that last sentence right there, hopefully gives you an idea of how these modes work. I said, if I wanted to use this mode, as in mostly these modes are personal preference. Just because you have a Cisco router doesn't mean that you have to use one of the Cisco proprietary modes. Or just because, you want to stay standards compliant doesn't mean that one standards compliant mode is better than the other. They all have some advantages and some disadvantages. Some will just flat out not work in situations, but overall, most of it is just personal preference. So let's get started by taking a look at non-broadcast multi-access. This mode is typically called non-broadcast mode for short, and this is the default. If you don't apply any other modes to the interface that you're configuring for, say, a frame relay network, it will assume NBMA mode or non-broadcast mode. Now, in this mode, non-broadcast means that no broadcasts are allowed and no multicast messages are allowed across the frame relay cloud. And that poses a problem because in the OSPF world, we use multicast for all our neighbor discovery and hello packets and so on. So instead of allowing the neighbors to discover each other, they have to be statically configured. And in this mode, you have to be using a single subnet for the whole frame relay cloud. Most people call that a point-to-multipoint style configuration. And it's actually one of my least favorite configurations to do because it causes all sorts of problems. But one subnet means that you have just one interface that is connected on router 4 that is able to reach multiple neighbors. Now, this mode acts like this is a LAN environment, which is good in ways and bad in ways. It's good because it allows the DR election to happen. There's a DR that will be elected, and you know the neighbors only form a full relationship with the DR, just like it is in a LAN environment. But the problem with that assumption, and the problem with it acting like a LAN environment, is that it's not a LAN environment. This is a frame relay cloud. In a LAN environment, router 2 and router 3 can reach each other directly. In a LAN environment, you can send a multicast message. So it's acting like a LAN environment, but really there's hindrances there that are not very LAN-like. So what I've done is I've configured our routers, I've pre-configured our routers to look like this, where we have router 4, 2, and 3 that are connected, no longer using sub interfaces. I actually have, let me on router 4, just do a quick show IP interface brief. You can see I've shut down all my sub interfaces that I've been using in the previous videos, and I've just consolidated all the configuration under serial 0. Now the way I've done that is by doing frame relay maps. I'm going to do a show run include frame and filter that down. Underneath the serial 0/0 interface, I've typed in frame relay map, and I've mapped the remote IP address to the local DELC that I used to get there. Now, if it's been a while since you've seen frame relay, this is a typical point-to-multipoint configuration, rather than putting it under individual point-to-point sub-interfaces. So router 4 has just one interface that it's able to use to reach router 2 and router 3. It's all one subnet, just like non-broadcast mode requires. So what I'm going to do is, now that I've shown you that, I'm going to begin my configuration over on router 2, which is the router in the upper right-hand corner. See its IP address? I'll do the quick show IP interface brief here. And you can see that we've got router 2 that is directly assigned that IP address on the physical interface. So let's set this up. I'm going to go into router OSPF1 and just type in a simple network command. I'll do network 10. Let's get really generic, 0.255.255.255, which will encompass all 10 interfaces, but these are shut down, so they won't be included in the OSPF process. I'll put everything in area 0. We're still just working in a single area. Now, I might as well assign a router ID while I'm here. Router ID 2.2.2.2. Now, this configures this router for the NBMA mode. And let me jump back here and do a show IP OSPF interface. When I do that, you're able to see, well, all of them are configured. You see all the sub interfaces that are running OSPF, but they're all shut down, so they're not really in action. The only one that's actively working is this one, serial 1. And you can see that its IP address is right here. The router ID is right there, just like I typed in. The network type, this is what I want you to see and compare it to the slide behind it. Network type is non-broadcast mode. Look at the hello timers. See that? We've increased to 30 seconds. Dead timer once every 120 seconds. Now keep in mind that one of the things that must agree for all the OSPF neighbors is the hello and dead timers. So you can't really mix modes in the sense that you can't say non-broadcast mode might be used over here and some other mode move over here, because many of them have different timers. I mean, just look above. We've got some point-to-point style modes up here, and those are running at timers of 10 seconds and 40 seconds as the dead timer. So this one is configured. Now, before we move on, let me talk a little bit more about these criteria on the screen. Router 2 is now set up and running OSPF in non-broadcast mode across the frame relay cloud. The first thing that you have to understand is with non-broadcast mode, it assumes multicasts are denied, so it can't discover its neighbors. I have to statically configure them. However, the good news is that you only have to statically configure them at one point. And that's typically going to be, in this style of design, at router 4. Because it's the only one that has full connectivity to all the routers. And I'm going to expand a little bit about what I'm talking about before I jump into the configuration. Static configuration of the neighbors means that I manually type in
Router 4, this is the IP address of your remote neighbor, so that instead of using multicast, it will use unicast to directly go out and reach router 2 over there on the right-hand side. Now, the other thing I want to talk about here while I'm standing on router 2 in the configuration is that the DR and BDR are elected, and the DR slash BDR must have full connectivity. Meaning, think back to when we talked about the DR and BDR in the concepts videos. One of the things I mentioned was if you had a bunch of routers on the LAN environment, meaning we had, let's say, 5 routers that are all connected to the same subnet like this. The only full neighbors that will form is the routers to the DR and the routers to the BDR. They will form full relationships here and then two-way relationships with the other ones because they don't directly exchange routes. All the information passes through the DR and BDR. Well, in the same sense here, the routers will only full neighbor connectivity, only, did I say full? Only form full neighbor connectivity with the DR and BDR because the DR has to be able to reach every neighbor. Now, there's only one router in this picture that can reach every neighbor, and that is router 4. So what I'm trying to say when I'm hitting this bullet is that not only must we say that router 4 must become the DR, we must have that being the DR. And I want you to think back to how we did that in the previous videos. We did that via the router priority. We said this priority is set sky high so that it's able to always become the designated router. But I want to take it a step further. And that a typical election means that there will be a DR and there will be a BDR. Now, in this picture, we don't have, or we shouldn't have, a BDR because there's no other router that has full connectivity to all its other peers. I mean, direct connectivity. So not only do I have to make sure that router 4 becomes the DR, I have to make sure that router 2 and router 3 do not become the BDR. And the way to do that, if you remember back from the previous video, is to go under the interface, and in this case that is serial 1, and type in IP-OSPF priority, which sets the election priority, and to set it to 0. To zero it out, to make sure my election ballot will never be cast, I will never be a DR or BDR. So now that that is done, let me jump over to router 3. Now I'll do a quick show IP interface brief just so we can get the view. Router OSPF 1. I'll set the router ID first to be 3.3.3.3. Let's do network 10.1.1.3, 0.0.0. Area 0 just to enable it on this one interface. I'll be less lazy, which means when we do the show interface, I won't get all of this other stuff for interfaces that I'm not using here. And then I'll go under interface serial 0/0, and I'll type in IP-OSPF priority 0 to zero that out, to make sure that router 3 also does not become a BDR because it does not have full connectivity. Do a show IP-OSPF interface. Sure enough, I see it is running in non-broadcast mode. My timers are accurate. They're matching the other routers. My router ID is set, and it's saying as of right now, no neighbors have formed because there is no designated router or backup designated router. Now let's set up the big guy, router 4. I'm going to come over here. Let's just clear off the screen so we get a fresh slate. And begin with router 4. First thing I'm going to do is a show IP interface brief, just so that you can see again, I've moved all the configuration under serial 0/0. I am able to reach the other two routers. I'll ping 10.1.1.3 and 2 because I have frame relay maps that allow me to reach them. So I'll go into router OSPF 1, let's set the router ID to 4.4.4.4, and I'm going to do the network of 10.1.1.4, 0.0.0.0, area 0. So we've got that configured. Now, because that interface is not, or I should say is, non-broadcast mode, it will not discover neighbors. I'm going to do a show IP OSPF interface, and I can see it's running, but as of right now, if I do a show IP OSPF neighbor, I get nothing. There's no neighbors that are configured. So I'm going to go back in and go under the router process and introduce you to a new command. You haven't seen this one yet. It is the neighbor command. I can type in neighbor followed by the neighbor IP address that I want to set up. Now in this case, I'm going to set up a neighbor statement for 10.1.1.2, router 2, and 3, router 3. So I'm going to come up here and say neighbor 10.1.1.2 space question mark, and you can see that we have the ability to tweak some of the factors for these neighbors. Meaning if I wanted to, I could specify individual costs. Remember, that's OSPF's metric to reach this neighbor. I could filter what sort of routes are able to reach those neighbors. I could say how often I want to set the poll intervals for, if I want to tweak my hello timers. I can also, and this is the big one that I always type in, set the priority of the remote neighbor. Now remember, the priority is its likelihood of becoming a DR or BDR. And I'm going to set that to 0. Now before I hit the enter key, you might be thinking, wait a sec, I thought we did that on router 2 and router 3. Why are we typing that in here too? Well, as the theory goes, Cisco says in their documentation that you should only have to type it in on one side or the other. Either here, put in priority 0, or under the interface on the remote router, put in IP OSPF priority 0. That's the theory. But I can tell you, in practice, I have seen it go weird if you don't put it in both places. Meaning when router 4 initially goes to contact that neighbor, it thinks, oh, well, you are the DR, you are the BDR because you have a higher router ID. It causes the neighbor relationships to kind of flap for a little while if you don't type it in under the neighbor statement. If you type it in under the neighbor statement, but don't type it in on the interface on the remote side, meaning you do what I have right here, but don't type it in on router 2 and router 3. I've seen it to where router 4 goes and contacts the neighbor, and then the neighbor tries to kind of overcome, like, overthrow router 4, like, no, I will be the DR, and router 4 is like, no, you can't be, and it causes neighbor relationships to fail. So again, in theory, you should only have to type it in one place, and sometimes that works. But in practice, I've seen weird stuff happen if you don't put it in both places. So I type in the neighbor statement, and I'm good there. I'll then type in the neighbor statement for 10.1.1.3, and I'm good there. I've now statically configured two neighbors in the OSPF process. Now I'm going to go ahead and do a show IP OSPF neighbor, and you'll see that as of right now, they are at the attempt phase. Now some people in the meaning it's attempting to become a neighbor. Some people will configure the static neighbor statements on router 2 and router 3, but that is not necessary. You can do it if it makes you feel better, but once you type them in into router 4 is the one that sends the hello message. Essentially, at that point, router 2 and router 3 just respond to that hello message. They don't need to have a static neighbor statement back. Now, I will also warn you that it takes a little longer. Now, you can see I went off the screen and took a little time because sometimes if you sit here, come back, you type in your neighbor statements, and you do show IP OSPF neighbor, you'll start going, oh no, it's stuck at attempt, and it'll sit there for like, I've seen 30 seconds, I've seen 60 seconds, and the reason I want to bring this up is because I know some of you may be taking this video in preparation for the CCIE Routing and Switching Lab. This is, out of the entire CCNP track, this series is one of the biggest ones to prepare you for the CCIE. You'll get the most information out of this one. So if you're in the CCIE lab, time is of the essence, and you'll start freaking out. I've been there. I know what it feels like. You type in the static neighbors, you hit Control Z, and you see it at attempt, and you're like, oh no, you clear the process. Attempt, oh no. And sometimes it takes a minute, and a minute feels like an eternity when you're on the clock. So sometimes it's best just to click off that screen, go configure another router, give it some time for those neighbor relationships to come up. Now the good news is that the neighbors have formed, and look how they formed. They formed as DR others, meaning that those are not designated routers and backup designated routers. If I come over to router 2, I can type in a show IP OSPF neighbor and see that it recognizes router 4 as the DR. So good news, we see that both of these neighbors are able to reach each other. Now with that being said, there is a problem. With the non-broadcast mode, let's do a show IP route. Show IP route. You know what's funny? You see this right here? I got a wireless keyboard, and sometimes I type so fast the wireless signal cannot keep up. So it actually missed the I. It makes me feel good because I'm thinking, wow, I can really type that fast that it can outrun a wireless signal. So I'm going to type in show IP route, and as of right now, it only sees the connected interface. Now, hmm, there's a problem. Meaning, let's look back at our network diagram. Well, let's do this. Let's do this. I'm going to add, just on the fly, I'm going to pause the recording and add a network here to both router 2 and router 3. This will help exemplify a little more. On router 3, I'm going to give it the, let's give it the 172.30.3 network. And I'll just give it as 24 mask. Router 4, I'm going to give it the 172.30.2 network. Okay, so let me pause the video. I'll add those subnets and then come back and take a look at the config. All right, I've added those networks and I want you to see the results. I'm going to come over to router 3, which, again, looking at the diagram, now has the 3 network and should be hearing about the 172.30.2 network, right? Well, let's check it out. I'll do a show IP route and, oh, well, that's good. I added the networks. Oh, and by the way, I added those to the OSPF router process via network command. So it's there. You see it right in the list. It now knows about 172.30.2.0. It's learned about it via its serial 0/0 interface. Well, that's great. Well, let me go ahead and do a ping there to that address. 172.30.2.1 is the router's IP address on the other side that I gave it. Hit the enter key and yeah. Yeah, that's not good. I'm failing here. Well, let's hop over to the other side and see if router 2 had any more luck. I'm going to do a show IP interface brief just so you can see I have added 2.1 to this side and 3.1 was on the other side. So I was pinging the right address. Let's do a show IP route over here. And I see that I've got 3.0 in the list. And let's try and ping it because it's learned it from router 3. So I hit enter and my ping is failing. Well, that's a problem. The OSPF is advertising the networks, but it's not for whatever reason able to ping those. Let's do one more check, right? Let's go over to router 4. Do a show IP route there. Router 4 should know about both of them, and sure enough, it does. Let's try the ping from here, 172.30.2.1. Hey, look at that. Great. Oh, 2.1 and 3.1. Hey, it's great. It seems like router 4 is the key router, right? It's able to ping them. It's just router 2 and router 3 can't. Here's the problem. Enough with the I don't even know what word I was trying to say. The shenantics, the shenanigrins, the shenanigans. Thank you. My wife helped me out with the word. All right. Over here, I've got router 3. The problem is actually exposed in the show IP route table. When I'm looking at this, I see the 172.30.2.0 network via, and look at this, the next hop IP address is 10.1.1.2. Well, let me see if I can even reach the next hop IP address. Aha. And there lies the problem of the non-broadcast mode, meaning it assumes that all of these routers can reach each other just fine because they're all one subnet, right? And if it acts like a LAN environment, then, I mean, in a LAN, that address should be able to reach that address because they're in the same subnet, they're plugged into the same hub, so the ping should work, right? Well, that's the problem. And to fix it, what we have to do is actually add a frame relay map. I'm going to type in a show run interface serial 0/0 to focus in my config. You can see that I only have a map allowing this router to reach 10.1.1.4 via this DELC. Now, what I'm going to do to fix this problem is go under that interface and say to reach, let me just paste that in, save myself a little typing, to reach 10.1.1.2, which is router 2 over on the other side. Look back at that diagram. To reach that router, I'm going to use the same exact DELC. So it's 2 maps pointing to the same DELC. It's a little weird, but it works. I'm going to jump back over to router 2 and do a show run interface. I believe it's serial 1 on this side. It is. I'm going to go under interface serial 1 and do the reverse config and say frame map IP 10.1.1.4. So I'm going to use the same DELC now to reach router 3. Before I just used it to reach router 4. Now, I'm going to go back and do a show IP route. And you can see that I still have the same route in my routing table, but now I should be able to ping. Let's first off try 10.1.1.3. Ah, life is good. And now that means I should be able to ping 172.30.3.1. Groovy. So that is the way to fix non-broadcast mode because, again, it believes or it falsely believes that everybody can directly connect to every other person. So we essentially have to trick it. We have to make router 2 and router 3 think that they're directly connected together when really we're just routing them through router 4. Now there's another mode that is industry standard that fixes all of those problems. That mode is known as point to multipoint mode. You can see the first thing up there is that it fixes the issues with NBMA networks. Those problems that we saw where we had to create the static maps to fix it, it will take care of those for us. Now the second thing is that it does still require a single subnet. So it assumes you've got a kind of a flat network, but it doesn't think it's like a LAN environment. As a matter of fact, it does not elect the DR and BDR. What it does is treat each one of these links almost like point-to-point links. All communication goes to the multicast address 224.0.0.5. The neighbors automatically form, so there is no static neighbor configuration that we have to worry about. So, and with the point-to-multipoint mode, everything takes care of itself. The only requirement that you have to have in order to run this mode is that your cloud must allow the multicast messages. And I shouldn't say the cloud because all service providers allow it nowadays. It's your router. Your router has to be configured to allow broadcast and multicast messages across the cloud. And let me bring the prompt back up. Get it centered up here on the screen. You can see that I'm on router 2, just where I left off. I'm going to type in that show run interface serial 1 one more time so that we can see the configuration. This is the keyword that I add onto all my frame relay maps so that my router will allow multicast traffic to go across that cloud. Now, what I am going to do to prove the effectiveness of this method is remove those frame relay maps from the configuration. So I'm going to go under interface serial 1, type in no, and paste that in there. So that, oops, that was the wrong one. Let me put that one back in. I meant this one right here. That was the frame relay map we added to reach the router 3 across the cloud. So I'll remove that, remove that one. And now what I'm going to do under this interface to change the mode is type in the command IP OSPF network. And notice I am under the interface. This is not something that's done from the router config mode. And I'm going to type in point to multipoint. You can see I'm now choosing a different network type. By default, this was set to non-broadcast so that it was a non-broadcast setup. Now, notice it did form the neighbor relationship one more time, even though I haven't changed anything on router 4. The reason why that is because if I type in show IP OSPF interface, I can see that it is now point to multipoint, but the timers are the same. That's the key element. The timers being the same is what allows the neighbor relationships to form. So now let me go over to router 4. And first thing I'm going to do is type in show run interface serial 0/0 because I'm going to remove the frame relay. Wait, am I? No, I'm not going to remove those. I'm going to go into the router OSPF. Sorry, I was trying to think of what I'm removing. I'm going to type in do show run include neighbor to show those neighbor commands in the running config. Because remember, I'm going to type in no again on this. We don't need to statically configure neighbors. Actually, I just hit the up arrow. We don't need to statically configure neighbors for the point to multipoint world. The neighbors will automatically form. So you can see that as soon as I did that, it shows the neighbors going down. That's because we haven't fully fixed the scheme yet, if you will. We have, as of right now, I'll do a show IP OSPF neighbor. We have the neighbors just going in the X star state is saying, I've lost the neighbor relationships. The neighbors are no longer statically configured. And poof, magically they came back online. I'll again tell you why that is in just a moment. Let me hop back over to the last router, router 3. And I'm going to do a show run interface serial 0/0. Go under interface serial 0/0 and remove, which one? This one. The static map allowing it to reach router 2. Put a no in front of that because I want to get that out of there. Point to multipoint fixes this, and now you'll get to see how. I don't know why I got out there. I'm going to type in IP OSPF network point to multipoints. Groovy. Now, just for good measure, you can see all the relationships go down. I'm going to come back over to router 4. Let me go ahead and clear the buffer, get a fresh slate, because I want to just restart the whole process. So I'll type in clear IP OSPF process. Yes, I do want to reset it. We should see the neighbors go down, and that will reset the neighbor relationships. Let's go ahead and wait because it takes a little time. I'm going to, as a matter of fact, while I'm doing that, I'm going to do a clear IP OSPF process on the other neighbors too. I do that just because I find after seeing and playing with OSPF enough that it's good just to restart the whole process after you change any modes, just because strange things can happen. So you can see that as of right now, we are currently in the init phase, the two-way phase. So as of right now, we're still kind of going through the forming of the neighbor relationships. Let me pause the video and we'll wait for those neighbors to come on full. It can take a full minute for that to happen. Then we'll come back and check out the results. All right, there we go. I'm going to do just, I guess, hit the up arrow, do that show neighbor command again. You can see that we are in a state of full. Let me jump over to router 3. I'm going to type in show IP OSPF neighbor, and right there, it's gone to full. Now, that's interesting because notice the DR marking went away. Remember, I said there is no DR BDR in this sort of process. So I'm going to type in a show IP route real quick because I want to see. Let's see. That's a problem. It's not what I was expecting to see. I wanted to see if the routes were being learned as of yet. The routes, as of yet, doesn't look like they've been learned. And one of the, I guess one of the issues I'm having right now is that router 4 is still seeing these guys as DR others. And in the true point to multipoint config, they should just be the little dashes as well. Did I type in the point, let me do this. Show run interface serial 0/0. Well, there's the problem. And that shows you what happens if you don't configure all the pieces. I need to go under serial 0/0 and type in IP OSPF network point to multipoint. I guess I didn't do it on router 4 because that, you can see, has reset the neighbor relationships. We've gone, at least on neighbor 3, from loading to full. And now I'll do a show IP OSPF neighbor. Good. There we go. That's what I want to see. And that will give you an idea of the problems that can happen if you have different network types configured throughout the network. Give it a little time. There's router 2. I knew he'd come along. And so we've got router 2, router 3 on the list. Now let's hop over to router 2 and do a show IP route. Oh, man. Hang on. Oh, there we go. Whew. See, I'm starting to freak out, panicking. Just took a little time for the routes to get over there. Look at this. We not only see the route. Sometimes I make myself laugh. We not only see the route 172.30.3.0. Now, notice we're on router 2. It learned the route from router 3 over here. So that route was advertised through router 4, back up to router 2. But look at how this happens, how it fixes those issues with the NBMA networks. What it also did was advertised individual statements saying this is how you reach the individual IP addresses all around the frame relay cloud. Remember we fixed this before by adding a frame relay map in there? We added frame relay map and added another map to the same DELC. Well, point to multipoint mode fixed that for us by advertising the individual IP addresses via the correct next hop IP addresses. So now I can ping, let's try it, ping 172.30.3.1 and hit enter. And it goes through because I can now reach that next hop IP address, reach the 172.30 network, because I now know how to get to that neighbor across the cloud. It takes care of it all for me. If I jump back over to router 3 and do a show IP route, I can see that I now have the network from router 2, but I also know how to reach router 2 individually via a host route. That's, by the way, a host route with a 32-bit mask that's being advertised in there. If it's still a little fuzzy what the differences between the modes are, go back. That's the beauty of CBT Nuggets. Rewind the video back to non-broadcast mode and look at the show IP routes back then. You will see that only this shows up in the routing table, and it will be via the wrong next hop IP address, and that's why we had to put in this static map going through. So that's, I personally, my favorite mode, if I must use a non-sub interface environment like this, is the point to multipoint mode, because it just takes care of everything automatically. Now that you've seen the RFC standard modes, these Cisco proprietary modes will go very quickly, as in, I don't even think I need to show you the config because you've got the concepts down. Cisco came out with point to multipoint non-broadcast mode, meaning that they said, well, the point to multipoint mode is great, but what if the administrator doesn't allow the broadcast across the network, which is what that previous mode we just saw requires. Well, this gives you all the advantages of point to multipoint mode, the one we just saw. But instead of allowing the neighbors to be discovered, we type in the neighbors statically. So the only difference is we do exactly what we did before. It's just we type in those neighbor statements, the same statements I removed when we went in there. And then we go into the interface. I'll go under serial 0/0 here. And the way we turn on this mode is we type in IP OSPF network point to multipoint question mark, and you can see add that non-broadcast keyword on the end of it. That enables the non-broadcast mode, which does exactly the same thing as the other one. You just statically type in the neighbors. The second Cisco mode is known as broadcast mode, and this one's really simple, being that if you go under the interface and type in IP OSPF network broadcast, it immediately begins treating the cloud like a LAN. You have to have one subnet and full mesh connectivity, just like a LAN, meaning you can't have this sort of hub and spoke topology. We've got to have, this kind of connection here because everything has to reach each other directly. It's the same thing as a LAN environment. You have a DR and a BDR election. Multicast messages are used across the board to communicate. So it is just like a LAN environment, and that is the broadcast mode. The last Cisco proprietary mode is known as point-to-point mode. In this mode, the Cisco router treats every single DELC, every sub-interface that you have, as an individual point-to-point link. And the secret is, this is actually the mode we've been using all along. When we first opened this video, I said OSPF supports 3 major types of networks. We had the multi-access broadcast network, a point-to-point network, and a NBMA network. The point-to-point mode makes the NBMA network act just like a series of point-to-point links. The key to this mode is that you need to configure your frame relay cloud in the correct way, meaning every single DELC that you have assigned in that cloud gets its own sub-interface. And in my opinion, this is the best way to configure a frame relay cloud. Doing everything under one big subnet, one big multi-point network is a nightmare. In the sense that it's just not logical. It has a lot of problems with things like split horizon. So using point-to-point sub-interface is usually the best way to go. And you've seen this operation all along. I guess I could show it to you, but I know this video is getting a little long already. But I just want to jump over to router 4 because that was, or sorry, router, which one did I do? It was router 2 that I configured all of those networks into the same interface. So I'm going to type in show IP OSPF interface, hit the enter key, and you can see that I have the point to multipoint, that's the main interface, but with all those shutdown interfaces, and I guess the loopback, you can see that they're all a network of point to point. And that is, going to use the hello timers of 10 with a dead timer of 40. This fixes everything. And in my opinion, this is the best way to configure a frame relay cloud, is with individual frame relay sub-interfaces. So with that said, those are the 5 modes of non-broadcast multi-access networks. The 5 modes supported by OSPF to work efficiently across that cloud.
As I mentioned before, I know this video is getting a little bit long, but before we wrap things up, I wanted to bring it back here to the 5 modes, just to show them all to you one more time. Because when I went through OSPF, I mentioned this was one of the most confusing parts of the entire protocol to me is what are these 5 modes about? At this point, you should understand that these are primarily preference. Some of them, yes, you have to do one way or the other depending on the kind of network design you've used. But again, remember, the network design is up to you. We saw non-broadcast multi-access, which is an RFC standard and is the default mode on the interface. This is where it treats the cloud just like a LAN, except all the neighbors have to be statically configured, and we get to choose who the DR will be. By default, it tries to elect them, but we want to make sure that the hub of the network, the core, is elected as the DR. Point to multipoint is one of my favorite modes. It is also an RFC standard, but treats all of the individual PVCs like individual point-to-point links, even though they're configured in a multi-point relationship. This fixes all the problems with NBMA mode, meaning it allows you to, or allows OSPF to replicate the next hop IP addresses for you, so we don't have to do those static maps to fix things like we did in NBMA mode. We then saw point-to-point. We just saw point-to-point, which was the Cisco proprietary method, where if you do use point-to-point sub-interfaces for frame relay, it automatically uses this mode and automatically fixes every problem you could dream of. This is by far my favorite mode. Broadcast mode is just like non-broadcast, except it sends broadcast. It does everything non-broadcast does. It's just a broadcast base to where you don't have to statically configure the neighbors. Finally, we have point-to-point, or sorry, point-to-multipoint non-broadcast, which is the same thing as point-to-multipoint. It's just now you have to statically configure the neighbors. It seems a little backwards, like Cisco took a mere configuration, but all their goal was to do is to give you more options when you're setting this up. On that token, let's wrap things up. We saw that OSPF supports just about any type of network you want to throw at it. Point-to-point, broadcast multi-access like Ethernet, and even non-broadcast multi-access. And the focus of this whole video was on those non-broadcast multi-access networks. The reason there's so much focus on them is there's so many design options. You have the partial mesh, the full mesh, the hub and spoke topology, and for each one of those design options, there's multiple ways you can configure OSPF. So we walked through all 5 of those modes, one by one, looking at the configuration for some of them, and putting together our understanding of OSPF over NBMA networks. I hope this has been informative for you, and I'd like to thank you for viewing.